Morning, everyone. I'm Rob Charlwood from Supercharged. Today, I thought I'd take a little bit of time to talk to you about site reliability engineering and chaos engineering. So I thought we'd have a bit of fun with this one and basically talk about how site reliability engineering, when combined with good chaos engineering, could have saved Jurassic Park. So first up, hands up if anybody hasn't seen Jurassic Park yet. Okay, warning, spoiler alert. Okay. Obviously, given the intended audience, I'm going to keep this section fairly brief, but for anybody that is new to SRE, I was just going to cover very simply what it is, the sorts of things that we do, and then that will tie in later with the case study on Jurassic Park. So, site reliability engineering, it combines various engineering disciplines to build and maintain reliable, resilient, scalable performance systems and services. So one of my favorite quotes on this was actually from an engineer at Google, which is class SRE implements DevOps. So DevOps being your underlying working practices, good collaboration, shared ownership, shared accountability, joint responsibility, and collaboration across all teams, getting rid of knowledge silos and things like that. And then SRE is effectively a way of working on top of that unlocks extra ways of working and extra principles to improve the way that your services run a little bit better. So we like to operate under the assumption that failure is inevitable. So everything that we're doing, we're building with failure in mind. We're always thinking, how can this fail? And actually, we want it to fail because when we fail, we learn. And when we learn, we actually end up loving failure and we actively go out of our way to cause trouble. Just to touch briefly on some of the stuff that we do, I'm going to keep this high level, not going to go into too much detail here given the nature of the audience. And this isn't an exhaustive list, obviously, but it just gives a high level overview for anybody that is new to SRE. So we define and manage SLOs along with that, and we do this by collaborating with key stakeholders and product owners to establish customer-focused service level indicators, service level objectives, service level agreements, and error budgets. These metrics are then used to measure the system's performance, but always from a customer's perspective. So when you're thinking about defining your SLOs, somebody actually gave a really good talk on this yesterday about how you define your SLOs, where you put your SLOs into your flow, and where you track your SLOs. Somebody actually did a really good talk on this yesterday. Apologies, I forget their name. But they should be done from a customer's point of view. What does the customer care about? If you as an engineer, you might care, I've got a Kafka cluster in my infrastructure, and I want to know if the queue is backing up and it's not being processed quick enough. Your customer doesn't care about that. Your customer doesn't know about it. All your customer knows is, does the service work? And so SLOs are designed to enable us to track customer happiness effectively and customer trust. So that kind of leads on to error budget management. The error budgets, which are based off of your SLOs, allow us to balance innovation and reliability by adhering to agreed upon budgets as defined by your SLOs. If you have an SLO that says, I've got three nines of availability, then you know you have 0.1% failure rate, or allowable failure, I should say. And what this does is it enables innovation. It allows you to be creative, and it gives you headroom to make changes without directly affecting your customer. So we partner with product owners and development teams to ensure that the correct choices are made as to whether they prioritize new features over resiliency, reliability, and performance improvements. So if they're burning through their error budget very quickly, then there's a good chance they need to stop development on new features and products, and let's focus on what matters to the customer, which is the service is reliable, quick, and doing exactly what they want it to do. We also handle incident response and management. So we develop and maintain incident response playbooks. We also handle disaster recovery and backups. We monitor systems to detect and respond to incidents quickly. And generally, after an incident has happened, we'll lead the post-incident reviews. So we'll carry out blameless postmortems, which identify the root cause, and then we help the service teams or any other teams that we might be working with write fixes that prevent recurrence of that problem. We automate operations. So we build automation tooling to reduce toil and remove manual intervention, especially in repetitive tasks. Humans are lazy. We don't like doing things over and over. And engineers are especially lazy. And it also removes the opportunity for human error. It's so easy to fat finger a command on a production database and drop all your tables. So we focus on things as code, infrastructure as code, monitoring as code, service as code, config as code. Anything that we can codify and version is generally really liked by SRE engineers. And we do this so that we can standardize infrastructure management, standardize infrastructure orchestration, and also standardize our deployment processes as well. We automate monitoring, logging, alerting, and scaling activities, and we automate the checking and enforcing of guardrails at different levels of the platform. So you might have certain security guardrails that you want to adhere to. I worked previously for a bank. They had a lot of security guardrails. You might have just config guardrails that you want to adhere to make sure that things are running in a certain way. And so we can check these at various levels. So we can check them during continuous integration, continuous delivery, while things are being built. We can also even do things at runtime, so we can actively monitor and check running services. Just touching on what we spoke about before. So monitoring, observing, and alerting. So we implement monitoring systems to track system health and performance. And we build dashboards and alerts to provide visibility into system behavior. If we don't know what our system is doing, we're in trouble. And everything that we do is based off of the quality of our data. We're making decisions off of the quality of our data. And if we don't have good observability, telemetry, metrics, traces, good SLOs, good meaningful SLOs, we're not in a position where we can troubleshoot or handle incidents effectively. So we spend a lot of time making sure that these things are correct within a system. I've touched on this before, but yeah, we implement the monitoring and tracking of the SLOs so that we know how the services are performing from our customer's perspective, not just what an engineer cares about. Is the customer currently getting a 10-second latency when logging in? We want to know. We also invest in observability tools to gain useful insights into log metrics and traces. So as you're probably all aware, we get data from all kinds of sources, all kinds of places, in all kinds of different formats. And in order to get the most out of that data, we need to be able to collate it, aggregate it, and report on it. So we spend quite a lot of time either using pre-existing tooling or building our own tooling that allows us to make better use of that data that we're getting in. And we also build high-quality alerting to bring the correct teams in at the correct times. So we don't want to be waking up somebody in one team at 2 a.m. if it's not even their service. So making sure that we've got the right things in place. Capacity planning. So we analyze system usage trends to ensure infrastructure availability and scalability. So there'll be certain days of the year where your service is especially busy. So in a bank, generally the last day of the month when people get paid is pretty busy. We tend to get about 28 million hits a day on logon. So you can analyze your trend, analyze your usage trends over periods of days, weeks, months, years, and see where those trends are. You'll still get the odd unexpected spike if something happened in the news and everybody tries to use the service. But by and large, you can get a good feeling of the hours of the day, the hours of the month, the week, the year that are most busy. We perform load testing and capacity analysis to avoid over or under provisioning. So we don't want to have too little resource provisioned. Otherwise, we're going to have very unhappy customers sitting around not being able to access the service. But we also don't want to over provision because then we're costing the company money unnecessarily for resources that are being totally underutilized. We optimize system performance to meet business goals. So specifically thinking about things like FinOps, certain service teams might have specific budgets that they have to adhere to as part of their projects. And so we can work with them to analyze their performance, see where they can reduce resource consumption, reduce compute in order to meet their budgets. We also ensure that the system can handle expected and unexpected spikes in loads. This kind of touches on what we talked about before. We need to be able to handle the days where we know we're going to be busy, but also the days where we've got no clue and it's just suddenly something's blown up and you're getting 28, 30 million hits. We build resilient systems, so we design fault-tolerant architecture to ensure high availability. We implement redundancy and failover mechanisms. I touched on this before, but we define and test disaster recovery plans, and we conduct chaos engineering experiments to test and improve system resilience and ensure that all the mechanisms that we put in place to ensure reliability work as expected. There's no point in having a multi-regional failover if you never test your failover. It might not work. So we want to make sure that those things that we put in place, if we're specifying multiple replicas of our service, are we getting multiple replicas? If we kill off certain number of pods within our service, does the service still respond? If we have auto-scaling on our Kubernetes nodes to handle spikes in traffic, does that work? When we throw load through it, Does it work? Does it scale up and back down? We need to know these things to make sure that the things that we're actually putting in place to ensure that we're reliable actually work. We also handle change management. So we develop automated and controlled deployment pipelines to reduce the risk from CI/CD changes, implement progressive rollouts. So for example, canary deployments, and handle graceful rollbacks if required. We actively review and test changes, and we monitor and track metrics such as DORA to measure the performance of our engineering teams. So it's really nice to know how well our teams are performing. So we like to know how frequently our engineers are deploying their services. If they're deploying 5-10 times a day, that's great. They're doing really well. But if they're only deploying once a month and they're deploying 10,000 lines of code, that's not so great. There's a bit of a smell there. Probably something that we need to look into. Lead time to changes. How long does it take code to get from GitHub all the way through to production? How quickly can we deploy features and products? Mean time to recovery. When things do go wrong, how long does it take to restore our service and bring things back to normal? And then lastly, change rate failure. So how often do our service teams deploy a change which breaks something? And these are all really useful metrics, not just for the engineering teams themselves, but also upper management as well, who want to be able to see where they can start to make improvements from a more strategic position. So, with all that in mind and a grounding in SRE, we're now going to take a little trip into Jurassic Park. As I mentioned, there are spoilers ahead. So what I'll do is I'll cover the disaster, what the problem was, and then the ways in which site reliability engineering and chaos engineering could have been used to mitigate either entirely or at least offset some of the problems caused. So, Jurassic Park's issues stem from a lack of resilience and reliability planning, lack of capacity planning, and a lack of testing which SRE and chaos engineering could have helped them to uncover early on before they opened the park and people got eaten. First disaster, human error and insider threats. So we've got a T-Rex hacking there. So Dennis Nedry was able to gain unrestricted root access to the park systems and was not confronted or held accountable at any point until it was far too late. So he had root access. He could do whatever he wanted. He had unilateral control over every system in the park. So how could we have fixed this? We could have used monitoring and auditing, and we could have also harnessed chaos engineering here as well. So we can use chaos engineering to run bad actor tests that check for resiliency against people trying to do things maliciously from an internal perspective, and also protect against bad configs, which comes back to the guardrails that we were talking about earlier. The chaos engineering might have revealed that they probably need to add in some security auditing and alerting. Certain systems, certain confidential systems with sensitive data, we want to know who's accessing them and when, and why they're accessing them. And if they're accessing something they shouldn't, we should be being alerted. Monitoring of critical systems. So, for example, the security camera system was shut down, allowing him to steal the dinosaur embryos. We want to know when those systems are being shut down and alerted. Role-based access control. So within their systems, they should have been giving engineers or people within the team the minimum required privileges to do their job effectively. And that kind of touches on zero trust policies as well. Assume that everyone is either malicious or incompetent, generally speaking. If they'd had these things in place, they might have caught Dennis Nedry before he even wrote the single line of malicious code. And then the continuous monitoring of the configs to ensure validity and compliance with the security guardrails. So making sure that people aren't changing configs that they shouldn't be, and making sure that people aren't turning off security cameras or turning off dinosaur fences. So that was then shortly followed by our power system failure. I'm quite proud of this slide because it works on two levels. It could be T-Rex, the band, or it could also be AC/DC, which I liked. So the problem. Loss of power causes critical systems like fences, dinosaur tracking, and security protocols to go offline. So we could have fixed this with redundancy, high availability, and failover. And again, chaos engineering could have been used extensively here. So we could have used chaos engineering to conduct power off and degraded power experiments to see where the weak points of the system are and expose single points of failure. That would have revealed, okay, we probably want to put in some backup redundant power supplies. There's no good just having one single power grid. We probably want some backup there, even if it's diesel generators. the ability for the power supplies to fail over to alternate power sources. If they're, I don't know, if they're running gas by default for their power or whatever it might be, can they fail over to some batteries that are charged by solar power or hydropower? The dinosaur tracking systems that are all built into the core platform, could they have had tagging into each of the individual dinosaurs with handheld battery-powered remotes that showed them where the dinosaurs were? Isolation of critical systems. As we all know, the velociraptors are rather nasty creatures, and you probably want them on their own dedicated power supply with their own dedicated backup, isolated away from the rest of the systems in the park. And systems spread across multiple data centers on or off the island, or even into cloud across multiple clouds. They had one data center, and when it went down, everything went down. So this was then followed by network and communication outages. So when the systems fail, communication across the park's various networks and departments break down. This isolates staff and leaves them unable to coordinate an effective response in the crisis. If people can't talk to each other, they can't fix a problem. So we handle this with incident response and management. And again, chaos engineering could be used effectively here to improve your processes. So we could have used chaos engineering to take down their primary communication network, to see how well their protocols and policies held up. Did people follow the guidelines correctly? Are the guidelines accurate? Are the emergency response scenarios accurate? Do the engineers do the right thing? And do they make good decisions during an incident? So having clear communication protocols, runbooks and playbooks, break glass and escalation processes. So most places, especially in somewhere like Jurassic Park, you'd probably want to put your production systems under break glass access for elevated access in emergencies. But by default, people have minimum required permissions. A backup communication process, this gets overlooked so often. When we think about how do we communicate at work, most of us are using Teams or Slack or some other chat-based variant. What if there's a massive power outage across all of London and Google, AWS, and Azure's data centers all go down? Slack, Teams all live on top of that. How are you going to communicate your outage? Can you get on a phone? But having a backup communication protocol, how do you talk to each other if your primary means of communication aren't there? High quality alerting, so we touched on this before, clear disaster recovery and backup protocols. And then this has been touched on a few times in various different talks, but having regular game days. You can combine chaos engineering with regular game days to test your flow from an incident from end to end and see how your engineers respond. So the next disaster we had was a failure in the containment systems. So the fences around the dinosaur enclosures fell without warning. This leads to a breakout of especially dangerous dinosaurs like the T-Rex and the Velociraptor. So we could have tried to tackle, or at least mitigate this, with SLIs, SLOs, and alerting. And again, chaos engineering could have been used. So it could have been used to run periodic fencing failure drills to see what happens if specific paddocks in the park lost power, and then prioritize which mitigation work to do. So if there's certain paddocks that are particularly susceptible to power loss, they could put extra resiliency in and redundancy in around those particular paddocks. SLIs and SLOs could have been used to monitor containment systems like the fences to ensure they are operating at a safe level. From a customer perspective, I don't want to get eaten when I'm at your theme park. And then alerting could have been put in place to notify the engineers when the power supply is degraded or unstable or disrupted. And that also applies to other things as well. So if they'd known or had more advanced warning of the storm that was incoming, they could have take some extra steps to pre-mitigate the problems, the extra problems that the storm brought. The storm compounded their issues and made things worse. So the next disaster was that everything was manual. So a large proportion of the park's systems are manual and require some kind of intervention from a human being. This obviously put the staff at jeopardy when walking across the park to turn the power back on with velociraptors loose. So as we all know, Mr. Arnold said, just got to walk across the park and flick the circuit breakers to bring the power back. And as we all know, it didn't end well for him. This then obviously allowed human error and to creep into the activities or decision-making at a time where people are under incredible duress. So when there's an ongoing incident, people are stressed. People don't always make the best choices, which is why your data quality needs to be so good, your monitoring needs to be so good so that you're making decisions based on sound data and not hunch or emotion. So we handle this, or at least mitigate some of this, by automating. So chaos engineering could have helped to surface and highlight some of the key steps within the Jurassic Park organization that were done manually. If they're trying to run a chaos scenario and they realize they have to run a script in order to allow part of the failover to bring the system back online, then there's an area there that they can focus on, an area that they can improve to automate and take away some of that manual intervention. So it also removes the chance for human error, removes duress and stress and poor decision making from the process. And also, computers are built to do repetitive tasks, and we're not really. And as a nice bonus, obviously it saves us engineers time and it saves Jurassic Park money. So, multi-system failures. So what we had was effectively a cascading domino effect of problems within the park. Started with the power shutdown, which is then followed by the network and communications loss, and then by the containment failures. And what this shows is that it just shows how vulnerable the park was to unexpected incidents and how tightly coupled and interconnected things were. So we could have handled this with chaos engineering. So chaos engineering allows us to carry out controlled experiments against our infrastructure in a safe way to allow us to quickly and easily find problems with our systems or services. As was discussed in one of the other talks, you can run this in production if you are mature enough and your SRE is mature enough and your chaos engineering knowledge is mature enough. I suggest starting out in a pre-production environment, somewhere where ideally that you can run load testing, because you want to run this under production levels of load. There's no good stress testing and chaos testing your system if you've only got one request a second going through it. So you want to be running this in an environment where you can run your load testing at the same time. What I love about chaos engineering is that it's really granular and very powerful. So tests can be run in parallel. So 3 things go wrong at once, or they can be run in serial. So one thing goes wrong and the next thing goes wrong, or they can be run in a mixture. You can basically mix and match however you want to create really interesting scenarios in which your services could go down. It's very powerful in that you can test individual components within a system, or you can test like entire user journeys from end to end. It allows you to prove your high availability and failover mechanisms work correctly. It allows you to prove your runbooks and your playbooks. It allows you to prove your incident response management, so how you communicate and the escalation processes. It allows us to find and address single points of failure. And most importantly, it allows us to expose interdependencies and likelihood for cascading failures. So we'll be able to see, by carrying out these tests, is there a chain here? Is there a knock-on domino effect? And how can we decouple those systems and make them more resilient within themselves? And as a nice side effect, you understand how your system behaves and responds in a controlled manner, and you learn a lot about your system. Even just running the simplest of tests, you can learn a hell of a lot about the way that your system works. So I'm going to leave you with Dr. Ian Malcolm. So life finds a way, but so does chaos. I do actually run some chaos engineering masterclasses. You can register for your interest using the left-hand QR code. And there is a masterclass happening in Bristol in May, where I'll be going into detail about chaos engineering specifically, live real-world scenarios. So please do register. And last but not least, I'd just like to thank SREday for having me. It's been really good. Feel free to reach out to me on LinkedIn. And I'll leave you with a final quote here. Chaos engineering teaches us a valuable truth. Stability is an illusion. Your system is one unexpected outage away from achieving true enlightenment. Thank you. Are there any questions? I'm not sure I've got time. I've got time. Oh, okay. Any questions? There's one at the back there.
Yeah, great presentation.
Thank you.
The only pity is that you didn't show that to the Heathrow team before the last Friday outage, but it's time to do that. One question, how many systems, components, application do you have in control? Yeah, so how big should be the system to consider it that it's really house engineering?
Oh, I see. Yeah, so you can run chaos engineering. My general advice is, even if you're like a small startup with relatively small services, get it in early get the benefit of it and start using it early. You don't need to have huge amounts of services for this to be justifiable. You can get away with doing it later. So if you're building a fairly new service or fairly small service, you could get away with just doing FMEAs and taking what you learn from those to like manually probe and write in mitigation or have smoke tests with it as part of your CI/CD pipeline. But if you've got the expertise and the time and the resource there, it doesn't really matter. You can start really small and then your chaos engineering will grow with you. Or as your systems grow and you find that you actually need it more, you can then look to bring it in at a later point. But there's no kind of like set point as to when you can use it, really. I personally prefer the earlier the better.
Okay. And last question, assuming that we are new to the chaos engineering, where should we start? What do you recommend?
One of the co-hosts, I think, wrote a book, which is quite good. I'm not sure if he's here. Yeah, so there is a book on chaos engineering. Where else? So I would start with just like picking maybe one of the open source tools. So you've got Litmus Chaos, you've got Gremlin, Chaos Monkey. There's a few kind of open source ones that you can use that are really easy to get started, and you don't need a whole bunch of expertise to use. The documentation on them was all pretty good. It's just, generally speaking, it's a case of installing an agent or an operator onto your infrastructure and then conducting your experiments. So you can get started pretty easily. Unfortunately, there isn't a whole lot of really high quality documentation available on this. I think it's still a fairly new area. It's also worth looking at there's a couple of books on system design. I'll see if I can find the names of them, but they teach you how to think about building systems that are resilient and reliable on a kind of larger scale, and it helps you to tease out the scenarios that you might want to test. But what you generally find is that if you're doing an FMEA on your service, you actually find that the things that you care about and you want to test actually fall out of that, and you can actually define them off of your FMEAs and start with those and then expand as your service grows and your maturity with chaos engineering improves.
Great. Thank you very much. Really great presentation.
Thank you.
One more?
I echo, it was a really good presentation indeed. I have the privilege to talk to a lot of SRE teams, DevOps teams, and it's interesting to see that usually they wait until an incident happens before they bring some of these principles and onboard them in their day-to-day. What sort of change in the mindset you think these teams need to have before waiting for an incident and apply it beforehand to prevent it?
Yeah, it's a good question. So I guess the biggest thing culturally is expecting failure, working with the expectation that your service is never going to operate 100%. Software engineers, it works on my machine, it's cool. They think it's just going to work flawlessly a lot of the time. And so it's about getting engineers that are writing the services to think about failure from the offset. As soon as they're writing their services, as they're writing it, thinking, how could this line of code fail? How could this line of code fail? How could this function fail? So actually getting them to start thinking as a team or a group of teams, starting to think about expecting failure at every point and trying to pre-mitigate it at every point. That's probably the biggest mindset shift outside of just having good DevOps practices within your organization, shared accountability, shared ownership, and shared responsibility. I think if you've got teams that are collaborating well and working well with no knowledge or less in the way of knowledge silos, it makes handling these sorts of incidents and implementing this sort of thing a lot easier, and you'll have less kind of pushback.